Hello everyone, welcome to course study on solid mechanics. In today's lecture again we will discuss the numericals based on Euler's formula. The problem statement of the numerical is as follows. An aluminum tube of length 8 meter is used as a simply supported column with two ends hinged carrying 1.2 kilonewton axial load. If outer diameter is 50 mm, compute the inner one that would provide factor of safety of 2 against the buckling. Take E is equal to 70 GPa for the aluminum and use Euler's formula. Okay, so as per the given statement, we have an aluminum tube of length 8 meter. It is used as a simply supported column. As it is a simply supported column with two end hinge carrying 1.2 kilonewton axial load. Okay, so from this the end condition is also given. Both ends are hinged one. It is subjected to axial load of 1.2 kilonewton. The outer diameter is 50 mm, that is it is capital D. Compute the inner one that would provide the factor of safety of 2 against the buckling. Okay, the value of E for a given tube is 70 GPa and they have asked to use the Euler's formula. Okay, so the given data is L, it is equal to 8 meter, so in mm it will become 8000 mm. Okay, the value of axial load is 1.2 kilonewton, so it will become 1.2 into 10 raised to 3 newton. The value of capital D, that is the external diameter, is also given. It is 50 mm. Factor of safety is 2 and the value of E is modulus of elasticity is 70 GPa. So it will become 70 into 10 raised to 3 MPa. They have asked to find out the value of small d, that is internal diameter. Okay, so the solution is as follows. First of all, the given end condition is both ends are hinged one. As both ends are hinged one, the effective length will be same as that of the length only. As both ends are hinged one, so the effective length is same as that of the length. Therefore, L effective is equal to L, which is equal to 8000 mm. Okay, then they have asked us to find out the value of small d. Therefore, we have the axial load given by crippling load divided by the factor of safety. The axial load can be given by, or we can see it as a safe load also. Safe load can be given by crippling load divided by the factor of safety. Therefore, from this equation we have the crippling load equal to axial load into factor of safety. Okay, so the axial load is 1.2 and the factor of safety is 2, so it will become 2.4 kilonewton. It will become 2.4 kilonewton. In Newton it will become 2.4 into 10 raised to 3 Newton. Okay, so we know the value of crippling load. We know the value of crippling load. It is 2.4 into 10 raised to 3 Newton. Okay, now by using Euler's formula we will find out the value of diameter, which is required one. Okay, so we have the Euler's formula, pi square EI upon L effective square. Okay, so the value of crippling load that we have already find out, that is PC, is nothing but crippling load is nothing but 2400. Okay, the value of pi square, as it is constant, it will remain as it is. Value of E is 70 into 10 raised to 3. Okay, value of I, we are not going to put the value of I because as it is a hollow tube, and in that particular hollow tube the internal diameter is not known to us. Okay, therefore we are not going to put the value of I, so it will remain as it is, and the value of L effective is 8000 bracket square. Okay, so from this equation, we have the value of moment of inertia. I is equal to 222327.63 mm raised to 4. Okay, and all of you know this is the value of I which we have find out from this particular equation. Okay, but the moment of inertia for a hollow circular section can be given by pi by 64 into capital D raised to 4 minus small d raised to 4. This is the value of moment of inertia for a hollow circular section. Okay, so we are going to equate these two equations. And for this equation we are going to put the value of capital D also. Okay, so on putting the value of capital D, on equating these two equation, okay, we will have d raised to 4 equal to 1.72078 into 10 raised to 3. Okay, so on calculating the value of D, we will have D is equal to 36.22 mm. We will have the value of D equal to 36.22 mm. Okay, so this is the value of internal diameter which we have find out from using the Euler's formula. Okay, so this is all about the numerical number 5th. Now we are going to solve a last numerical based on the concept of Euler's formula and the limitation of Euler's formula. Okay, so the problem statement is as follow. Determine the slenderness ratio at which the Euler's formula for a fixed end can be used. Take E is equal to 200 GPa and the proportionality limit equal to 250 MPa. So as per the given statement, we have to determine the value of slenderness ratio, that is lambda, and lambda is equal to L effective upon K. Okay, at which the Euler's formula for a fixed end can be used. So the end condition is also given, it is a fixed end. Take E is equal to 200 GPa and proportionality limit equal to 250 MPa. So this proportionality limit is nothing but it is the value of crushing stress. Okay, therefore we have E is equal to 200 GPa, so it will become 200 into 10 raised to 3 MPa. Proportional limit will be 250 MPa. We will be consider it as a crushing stress. Therefore, we have the formula L effective upon K greater than or equal to under root of pi square E upon sigma E. Okay, therefore as it is greater than or equal to, so we will equate these two equation. We have Le upon K which is equal to under root of pi square into E is 200 into 10 raised to 3 divided by sigma E is nothing but 250. Sigma E is nothing but it is 250. So on solving this particular equation, we have the value of lambda 88.86. 88.86. So what does it mean? It means that if you consider the value of lambda less than 88.86, if you consider the value of lambda which is less than 88.86, then it will be considered as a short column, and for that case, for that case our Euler's formula will not be applicable. Okay, so for a given condition, we have to consider the value of lambda which is greater than 88.86, and then only our Euler formula will be applicable. Okay, so this is all about the numerical based on the Euler's formula, its limitations, and the numerical based on the shape load also. Okay, we will stop here. In the next lecture we will discuss the Rankine formula. Okay, so we will stop here. Thank you.